Hello and welcome to Build Your Own CPU Part 9. In this episode we'll take a deeper look at a control bus. Now to help test the control bus, I built this 64-channel logic analyzer. This is because there are lots of signals to test. There's around 100 different instructions with all their addressing modes. There's 13 steps to each instruction, and each step has got 4 different states. So that's thousands and thousands of tests. So to do that with a multimeter or an oscilloscope would be very, very laborious and time consuming. I built this partway through the project so I can just plug it straight into the control bus with all these connectors. As we saw in the last episode, I put pins on the end of the control bus so we can connect it up. And this feeds via the serial port here direct into the PC, and I wrote a piece of software to display what the signals are doing. I'll show you later in this video. Now this logic analyzer is made up of, it's going to be pointer stick, this PIC chip here, which is a PIC 24F16KA102. It's a 16-bit PIC chip, fairly cheap. I use this one because I've got a bunch of them left over from previous projects. And here are just some TTL gates. It's what model that is. That's a 74AC573. I got some of these for another project, and in fact I got a job lot and I've got literally hundreds of these. So that's just 8 bits coming in, 8 bits out into here, and I can switch between each of these inputs to feed this. So that's 8 inputs there, 8 there, 8 there, 8 there, that's 32. As you can see, there's 2 layers to this. There's another board underneath with another 8. There's only one of these chips though. The signals feed through up here onto the lower board to feed the signals back up. So this PIC chip basically just samples all 8 of those inputs and feeds them out serially through this little serial to USB adapter that I got off eBay. We'll go into the circuit of this a little bit. Here's the circuit board. Here we have there's 2 boards that are identical. It's all on one board, so it's cheaper to make. And I've got a limit of 500 points I can do on a board anyhow, so that's 500 there, 500 there, because if I wanted to do the whole thing in one, that would have been way in excess of my limitations that I've got. Oh, turn it up the other way. It's the same as that one. So there's there, chips here. This is the programming port, and that's the main PIC controller sits there. Now these 2 boards are identical, but what you do is on the bottom board, these jumpers are jumped across here, and what that does is it connects a different 4 pins coming on the PIC chip, I/O pins, out onto the control signals of these. They all come up on the same bus. So these will be chips 1 to 4, and that'll be 5 to 8. I've got 8 different chip selects coming out. The chip select signals actually feed down here onto the bottom board and then linked across there. And the bottom board just doesn't have that chip on it at all, or any of these other components. Over here we've got a 3.3 volt regulator, because this is all 3.3 volts. So we have 5 volts is fed from the USB adapter here. The serial is a 5 volts output here. It feeds out onto the board with the regulator. Oh, you just about see the regulator underneath there. I'm getting it on the camera. There's just a little regulator, 3.3 volt regulator there, and a capacitor. And that feeds all the rest of the circuitry. Now the reason it's 3.3 volts is because this processor is 3.3 volts. These ICs can run off anything up to 6 volts, but then go down to 2 volts as well, so they're fine. The signals coming in will be 5 volts. I've got Zener diodes and resistors feeding them. We'll look at the circuit diagram in a moment. There's a few spare connectors there in case something went wrong. I could modify it. I did make a mistake, hence lead off here. And this jumper here, that is just turns the supply off to that PIC chip. because programming a PIC chip with a supply onto it is sometimes a bit fussy. So I always put a jumper there, so when the program is plugged in here, I can program that direct. And these components here is just for the programmer. Now this lead here, I kind of forgot the 0 volts, and you need 0 volts if you're going to measure anything. I've redesigned this board with a couple more pads at the end here, giving some pin out for 0 volts, so you don't need this bit. Here we have the circuit diagram. This is the actual microcontroller. So data bus going in here. Here's all the jumpers. We jump across to the other board to selecting different I/O that are used for the chip selects, regulated supply. This is all the programming ports, and these are the actual inputs. So we've got, if we just look at this one here, that there is the 74573 for buffering the input. So we've got an output enable, and we've got a latch enable, that's on the input. So the microprocessor will do the latch enable, which will read all the inputs on all 8 chips at once, and that data will just be latched in here. And then it will go around and do the output enables one at a time, put the data onto the bus, fetch a read in and send off to the PC. Now the inputs, as I said on there, this has only got a 3.3 volt supply, so we mustn't put more than 3.3 volts on the digital inputs. So here's the actual input, and that feeds through a resistor. Then there's a Zener going down to 0 volts. So we've got a 1k resistor there feeding a 2.7 volt Zener. If you look up the spec sheets on the Zener diodes, you'll find that they actually start conducting at a higher voltage. So 2.7 is just a nominal voltage. So the spec on this one shows that the current flowing through there of about a milliamp, that will have about 3 volts on it, which is fine. If I picked a 3 volt one, it was more than 3.3 volts, which I was a little bit worried about. So 2.7 was ideal. So I can put on here, if you work out resistance and current flows, etc., about 40 volts on the input of this before this dies, which was fortunate, because I mentioned earlier that I did put 40 volts onto the whole board, and this I believe was plugged in at the time and it survived as well. So 8 channels there, identical on both boards. This is a schematic of the input IC on the logic analyzer. As you see, it's an 8-bit chip. On the left over here we've got the latch enable, so the data comes in D0 to D7 at the top. We strobe the latch input enable and do this on all 8 chips, so we've got 64 bits all latched in at the same time. And then the microprocessor, the PIC chip, will one at a time do an output enable onto its data bus and read the data in that's been saved in there. The bottom 4 bits will be the first nibble, and the top 4 bits will be the second nibble. Here's the layout. So we've got that 74AC573 input IC, and we've got 8 of these spreading down. So there's 1, there's a second, and 6 more. Input 0 comes in here, all the way up to 7, then input 8 is on the next chip, and so forth. And these feed out onto a bus on that card. So the PIC chip will select this IC, reading in all 8 bits, and then it will spit it out as a byte. It'll do 16 bytes every cycle, because there will be 2 bytes per IC. So the first byte, this bit here will be 000, that means it's nibble 0, and there's the actual inputs, values will be sent. And then the second byte will be the second address here, so that's address 1, and that will be 4 to 7. Then we'll have address 2, which will be 8 to 11, then address 3, so forth until we've gone through all of them. The data bytes are formatted like this, so we've got bits 0 to 7 of the byte, and the top 4 are the nibble address, and the bottom 4 are the actual nibble. If you imagine we've got that number come in to the COM software I showed a bit earlier, we'd have the address at the top and the data at the bottom. So that happens to be address 11, so it's a nibble 11. So that would be inputs 44, 45, 46 and 47, whether they're on or off. An easy way to calculate which is which on these is the nibble number times 4 tells you the first input, so it's input 44. So if that was a 15 there, 15 times 4 is 60, so we'd have 60, 61, 62 and 63. And then it will just cycle around to the next one. It just keeps cycling, and I've set it to cycle around once a second. You get all the inputs every second. I could reduce the timer and make it spit out faster. And this is coming out a 115,200 baud. I could speed that up as well to make it run faster, but this was more than fast enough for what I needed it to do. To display this data, I wrote a simple basic program that receives the bytes from the logic analyzer, decodes them, and then displays a piece of text in the box to say which bits are on or off. We start at the beginning. We've got an array with all the channel names in. So you put whatever text you like in, like carry input enable, input register, input enable, IO, be clear, etc. And you connect that channel input to that control signal on the motherboard, or on the control bus, I should say. This is just building up the picture. We'll run the program in a moment. When we actually get data in, comes in here, it just receives a byte, there's your input, and we just AND it to split off the address and the data. Then if the address is 0, then go to address routine 0, where it chops off the individual bits and prints the actual data to the screen. So if we actually run this now, we have just a simple screen like this. We can select which channel the data is coming in. I'll just put 4 COM ports there. And when the particular input's on, we'll see that a name comes up here. The string that we entered right at the beginning will come up in these. So there's 64 channels in all, 0 to 63. And we're on COM 3. This listed here is the data coming in, and there's the addresses decoding and the data that's on it. As you can see, you've got different signals turning on and off. There's the control signals. I've just got the processor running in auto at the moment, so it keeps changing. It updates once a second. I've switched the CPU to single step mode so we can go through a quarter of a step at a time. So if we run the program, here we go, we're on COM 3. And that's the first bunch of data coming, so it automatically comes in. I've reset the processor as well, so everything's in at 0. Now what we should see, if we look at an instruction, on step 0, we should have the A input enable on, the program counter output enable on, and the memory address register input enable on. So we're going to move the program counter into the memory address register and into the A register. So we flip back to the program. And if I step back on one step, so this is T0 on, we've got program counter output enable on, memory address register input enable on, and A register input enable on. I'm afraid I can't get them both on the screen at the same time. So now we do first pulse, it's quarter step. So pulse comes on, that enables the signals into these registers. And if we press the F3 for turn the pulse off, that's now locked in. We go F4, the T0 is turned off. So we've done all of the T0 steps there. The next pulse, so it's T1 on. We should have adder output enable on, program counter input enable on, because we put in the incremented value from the adder into the program counter. And at the same time, we'll be sending the memory address, which is the memory address register output is on all the time. That's going out onto the address bus, and we'll have the instruction register input enabled, so the actual instruction that's in memory gets loaded into the instruction register. We've got the C register is set, so it does the increment for on the adder for the program counter. The memory chip select is on because we need to read from memory, and we're doing a read cycle. Oh, and the B register is cleared to do with the increment. Been through that before. So if we go back to the actual screen, we've got instruction register input enable, B is cleared, C is set, doing a read, coming from the memory, program counter input enables on, adder output enables on, and we happen to C register output just happens to be, well, we've set it so that control signal's on as well, because that's feeding round to the adder. And we've got 1 on the data bus, internal data bus that is, because that's the new address that's being loaded into the program counter. So if we go back to, oh, wrong one, that one. Yeah, we don't want that screen. I'll press F2 to turn the pulse on. That enables all the signals going to the registers. Pulse off, and then, oh, it's a bit sticky on that one. That's it, and T1 is turned off. Now, I'm not quite sure which instruction this is off the top of my head, so we may or may not get something on clock 2. Let's have a look and see what we get. So if you know the instruction, you go for it. So we got T1, T2, sorry. Oh look, and we're doing the same again, we're going to increment again, so we've obviously got this addressing mode turned on, whichever one it is. Pulse on, as you can see up here, and we do pulse off, and then we do T2 off. So we've got T2, we must have a T3. So I've programmed the motherboard when it reads the keyboard for F1, F2, F3 and F4 are doing the steps, tells it to go through each quarter step of the clock. So F1 on again, so we're now on T3, which should be adder out, program counter. That's just a pure increment it and move it into the program counter. So there we go, just those signals on, and it's a number 2 this time. We've incremented the program counter. Pulse on, pulse off, end of T3. We got a T4, yes, we've got T4, and it goes through the same things again. Alright, so this is actually now loading data in, so this is the data that's coming from memory. So if we look at T4 on here, we've got into A, loading data, input enables, we're loading data in to the A register, and that's it. Oh, sorry, T4, data in A register from memory, and it's a read. Back again, there we go, read, memory to select, data in, that's the data into the CPU, so we're connecting the external data bus and the internal data bus, or join them together going inwards to the CPU. A register input, and I've turned the pulse on, so that data now has moved into the A register. If I pulse off, that should now be locked into the A register, and then T state off. And we're now at T state 5, and that's going to be moving, here you go, A output enable, that's going to be moving the A register output enable into the memory address, because what we're doing is that byte of data we got in was actually the address of where the data is being saved. We're obviously doing a memory addressed read. Pulse on, pulse off, and finish that cycle. There we go. So it was T5. Now T6 will, depends what instruction we are. I'm not quite sure what instruction we're on. Let's press the buttons and we'll see what we get. So T6 on. We're doing a B input enable. Oh, there we go. Yeah, T6 is normally loading the B register. So we want B register input enable and the data input. So we've put the address of where the data is in the memory address register here. And now we're going to, so that's the address is now pointing at where the data is. So we're now going to actually load the data in, memory chip, read it into the B register, which is mostly what step 6 does. So B register in, data input enable, memory chip, read, press pulse on. We're reading a 0 in because all the data channels are off. Pulse off. And end of that cycle. So that's T6. And we'd carry on going through all the others the same. So if I press it again, we won't do T7 because that doesn't do anything. We'll go straight to T8, which is the addressing modes again here, which is very similar. The 2 to 4 and 8 to 11 are the same. That one just does the first source, this does the second source. We go back to there. And it steps through there again, read number 2 in, and T9, incremented it, the address back out, it's T10, so you can see we can step through each little bit at a time. Must be a slight little bug in my code because pressing F4 seems to take a little while to react. Well, it could just be the voltage on the keyboard, which we'll cover on another episode, how that works. This is 12. 12, obviously not doing anything on this instruction. Come on. There we go. This must be T14. Doing a B out. It may not be this instruction. B out to data out. Let's see what happens. See if I've got the right one. B out. Oh, there we go. So we're doing an IO. This must be a write. Oh, of course it is, yes. The very first instruction on what I've got programmed in there is to write a value out to one of the paged memory slots. So we've got IO, it's turned on. Let's find the IO one, shall we? So recent, there should be one called out. I've got it here. Yeah, there we go. We must be using that one. So here we go. We've got a B out, data out enable, and we've got the IO signal is turned on. Let's zoom that in a little bit so we can see better. Scroll that across. So we're moving the B register, which we loaded earlier, into the IO, which was already set up on the memory address. On one of these, I don't know which one. Must be on that one. So yeah, there's where we loaded the B register on step 6. There's no 12, there's a T14. So there we go. Telling it IO, we're doing the data out, coming out the B register. There's the pulses on. Pulse off, so that would have been written out. And the end of that instruction. So the next instruction will be background to a T0 again. As you may notice, here we go. You may remember those values. T0. You'll notice that this instruction, the out instruction, is very similar to the how do we switch to the other one? You notice it's all very similar to the move instruction. All these bits in here are just the same thing again and again. You're just setting up the memory address to load the data in. So 6 is getting the first bit of data, 12 is getting the second bit of data, and 14 is actually executing it. And the green bit is load the instruction. So it's all modularized. And that's how that bit of software works, but it allows you to see all these control signals, and I can go through every step of every instruction, which I did, and see all the signals coming in or not coming in, wherever they should be. And that's testing the logic of the instruction decoder. We'll go into the fine details of each instruction decoder card in another video. Now here we can see the logic analyzer connected up onto the control bus. Now all those resistors and Zener diodes on the inputs actually tie the control bus down a bit, and I didn't really realise this to start with, and then I got everything working like this, and then when I disconnected these leads, because I thought, yep, it's all tested, all working, so we pull off all the logic analyzer pins, okay, just to put on. And if you look close up on here, yes, before I stick, you can see these termination resistors underneath. Well, they were 100k, and I'd unplugged it. Then I wanted to set it running, and it just went loopy and was doing all sorts of different things. And I thought about it, it was working with the logic analyzer plugged in, but not with it unplugged. And I remembered those resistors and the Zeners, it was pulling the signals down. So I've done a little test and I found out that these resistors need to be lower. At the far end on the control signals, I was getting very short pulses of about 25 nanoseconds, which was turning registers on and off when they shouldn't have been and changing their data, and that's why it wasn't working. There's a sort of ringing signal on there, and I believe that's the length of the buses. All the inductance and capacitance in the wiring and the boards was causing it to ring a bit. So on the bottom here, on top of all these 100k resistors, I actually soldered a 5k resistor on all of them, because I knew it worked with the 1k and Zener diode on the logic analyzer. So I thought I'll try a 5k on there, which worked a great deal. There was still a little bit of noise, and on the inputs of the cards, let's move the camera over. As you can see here, might be a bit dark. On the inputs of the register, this is register A, got these resistors up here instead of links. So there's one link there, that signal's fine. But these signals here, some of them had ringing on them. So there's a resistor, 1k resistor, and a 1 nanofarad capacitor on here, on each of them. So that's an RC network it forms. So the signal comes in and that capacitor's down to 0 volts. So it's a little filter that filters at about 1 microsecond. So I cannot go faster than 1 microsecond, the pulse on and pulse off, but this board doesn't run anywhere near that fast. And I've basically done that. And every control signal, as you can see on the status register, there's quite a few of them. And I had to modify the actual circuit board to include these all on the board. So if you used to build one of these, you wouldn't have to put these links in. That's noise on the buses, on these control buses up here, turning things on and off when they shouldn't do. And I sort of bodged around it. But they are, if you look back here, is a long run for all those signals going across there. So you expect to get a bit of noise on there. Well, that concludes this episode. In the next episode, we'll be looking at the actual instruction decoder board, T-state boards, and the logic involved in them, and how the instructions get decoded by them. So don't forget to like and subscribe, and tell all your friends about this channel.